welcome to our presentation on MPI, MapReduce, and Cuda for today's AI applications. In this project, we'll take a closer look at how these three important technologies are used to meet the growing computational demands of artificial intelligence. Artificial intelligence is expanding faster than ever, and traditional computing systems are struggling to keep up. As models get bigger and data sets become more complex, we need better ways to train and deploy AI efficiently. This project focuses on three main technologies that are helping to solve this problem: MPI, MapReduce, and Cuda. MPI is widely used for communication and distributed AI training, but it has key problems like poor fault tolerance, fixed resource requirements, and scaling issues at large sizes. While techniques like checkpointing and hierarchical all-reduce have helped, they don't fully solve the issues. Checkpointing isn't always seamless, elastic scaling is still difficult, and hybrid communication methods aren't widely adopted yet, leaving current MPI solutions with serious limitations. New solutions focus on adding better checkpoint recovery, enabling elastic scaling, and using hybrid communication to improve efficiency. High-level MPI APIs also make distributed training easier to manage. Together, these changes reduce downtime, improve hardware usage, speed up communication across clusters, and make large-scale AI training much more practical and reliable.
The main MapReduce problem is that AI pipelines are often bottlenecked by the data preprocessing phase, including clearing, transformation formatting, and shuffling of massive datasets before we can even train the model. Some of these solutions, such as standard MapReduce, Spark, and Accurate ML, creates redundant I/O delays, overuse in memory, and instability in large scale. It doesn't focus on preprocessing quality and fault recovery, causing the system to retrigger rather than only the partial recomputation. This leads to our own solution, which is Parallel MapReduce, a specialized extension of MapReduce that is designed to parallelize AI data preprocessing across clusters efficiently. This solution mainly works since it reduces redundant I/O by persisting intermediate results, parallel data cleaning, and transformation within built-in AI plugins, and incorporating dataset partitioning awareness. Overall, this system should improve by 2 to 4 times versus the older solutions, since it's also applicable with Apache Hadoop 3.0. However, they use HDFS for caching and Java for preprocessing logic, while we would using Spark, and ours would be built in. Our benchmarks and applications are mostly ImageNet, Cocoa, Wikipedia dumps, and tabular datasets, enabling faster and more efficient data pipelines.
Cuda problem and solution limitations. While Cuda has been critical for accelerating AI workloads by enabling massive GPU parallelism, it also comes with important limitations. One major issue is vendor lock-in. Cuda only runs on NVIDIA GPUs, limiting hardware choices for developers and organizations. Another big challenge is that CUDA programming requires deep knowledge of low-level GPU operations like thread hierarchies, memory structures, and synchronization. This deep learning curve can slow development and restrict access to high-performance computing. On top of that, manual memory management often causes fragmentation and inefficiencies, leading to out-of-memory errors during large model training. Scaling across multiple GPUs is also tough without heavy manual optimizations to fix bottlenecks like memory transfer delays and poor kernel scheduling. As AI models continue getting bigger, these challenges risk slowing innovation and driving up costs. Solving them is crucial if Cuda is going to stay practical for the next generation of AI. Our Cuda solution and how it improves. To make deep learning development faster and more accessible, we propose a high-level Cuda abstraction layer. The system would automate memory management, fuse adjacent kernels to cut overhead, and optimize training for FP8 and FP16 precision. It would also make scaling across multiple GPUs much easier by integrating NCCL. Benchmarks suggest this could speed up training by 30 to 60% and reduce GPU memory usage by up to half, allowing developers to train larger and more complex models. Beyond just performance, it would also lower the barrier for researchers and engineers who don't have deep CUDA expertise. By removing common bottlenecks like memory fragmentation and inefficient kernels, this platform would help more teams deploy advanced AI models quickly and reliably.
MPI, MapReduce, and Cuda are essential building blocks for large-scale AI systems, but they each face challenges when used with modern workloads. By addressing issues like fault tolerance, flexibility, memory management, and distributed optimization, we can significantly improve their performance and usability. Our proposed solutions show that with targeted improvements, these technologies can continue to support faster, more scalable, and more accessible AI development, helping researchers and engineers meet the growing demands of the field.
Here is how the workload was divided amongst the group. The study components of MapReduce and how it relates to modern AI was Xander, the study components of MPI and how it relates to modern AI was Sean, and the study components of Cuda and how it relates to modern AI was Alice. We all determined their overlying purpose and how they best advance modern AI problems, studied the solutions on all these facets, and combined them to determine an overall solution to help advance modern AI, and we all combined our findings and formulated a research paper and presentation.